Finally, we get down to the contribution due to V4, and we should get the result of V4 divided by 16. So here we set B1, B2, B3 switch connected to ground, and B4 connected to V reference as shown here. So redrawing this circuit as we did before, we have V4 at one end, and then I labeled here Vx, Vy, and V4 prime, and V4 prime is the input to this inverting amplifier or summer. So here, connected to the other end of V4 is Vx, and Vx is connected to the 2R, and that's shown here. Now connected to the other end of Vx is Vy through the resistor R. That's shown here. Alright, and then this we have a 2R connected to ground due to V3, and that's shown right here. Now connected to the other end of this resistor R is V4 prime. So here's V4 prime, and connected to V4 prime are two resistors 2R and R. At the other end of this 2R is connected to ground called V2. So that's shown here. And then connected also to V4 prime is R. At the other end of R is connected to the virtual ground A, and that's shown here. So we redraw this circuit, and that's shown here. Now doing the same analysis we did here, we find that this resistor network is 5/3 R, because this is 2/3 R plus R is equal to 5/3 R. And then this 5/3 R is connected in parallel now with this 2R, which is equal to 1011 R, as we calculated earlier before in the previous, just earlier. Now this resistor network is all equal to 1011 R, and right here from Vx on, this 1011 R now is connected in series with this R colored in green. So R plus 1011 R is equal to 21 R, and now this resistor network is 21 R in parallel with this 2R also colored in green. When you do this algebra, that's 42 over 43R. Okay, just multiply these two resistors, 2R times 21R, and divide that by the sum of those two resistors. And when you do that, we get 42 divided by 43R. Now we can use a voltage divider. V4 2R divided by this resistor network of 42 over 43R. So here's our voltage divider. That will give us Vx right here. Alright. And when you finish this algebra calculation, we have 21 over 64 V4. Now Vx in terms of can be used to calculate Vy shown here, because that's our voltage divider input Vy right here. And we can use that as an input to do a voltage divider. So Vy would be 21/64 V4. That's what we calculated earlier right here. And that serves as the input, so we can calculate Vy, and we know that this resistor network is equal to 1011 R, and so you divide that all over 2111 R, in which we found that network right here, calculation. So it's R plus this resistor network of 10/11 R. So 10th 11th R divided by 21 over 11th R, and we get a result of the following. Then we use this result to do a voltage divider for V4 prime. So here's our 21/64, here's our 10/11, And now we just do finally one more voltage divider right here, in which we have 2/3 R divided by 5/3 R. Now when you do all this algebra calculations, you can see a lot of things cancel. The 3's cancel right here. The 5 and the 10 cancels to 2, and the 21 cancels. And we have V4 divided by 16. And our current contribution, ISC4, is just V4 divided by 16R. So we finally proved that all the current contributions due to each input is ISC1, ISC2, ISC3, and ISC4 is equal to V1 divided by 2R, V2 divided by 4R, and we just did V3 divided by 8R, and V4 divided by 16R. And all this can be simplified such that our output voltage, since this is like an inverting summer, can be connected to a V reference, or where the switch B1, B2, B3, and B4 controls the switch, and that's described by this equation. It's either not connected to the V reference, or it is connected to the V reference. So this BK again is connected to one or two values. So that concludes finally the R-2R DAC that we just calculated. And it turns out to be equivalent to the binary weighted DAC. Hopefully that wasn't too painful, but that's the analysis, and that's a good review of using superposition. Again, the R-2R network is used in place of the binary weighted because there's only two values of resistors, R and 2R, which simplifies the fabrication and hence the cost. So once again, in summary, we have our V output of this digital analog converter described in terms of the binary inputs B1, B2, B3, B4 that is weighted by respectively 1, 2, 4, and 8, multiplied by some constant K. In this case, the K is negative RF over 2R for this R-2R ladder network. And we multiply that by a V reference voltage, which governs our range for our inputs. So here we have this equation that describes this circuit configuration to implement this digital to analog converter.